All right, in the last section we saw one way to multiply two vectors, and we ended up multiplying them, so to speak, and we use that dot product as a multiplication. This section, 11.4, is about the cross product. And like the dot product, unlike the dot product, when we did a dot product, we got a scalar when we were done, one single valued number. When we do a cross product, we actually get a vector. So we actually have to start a little bit further back with something called a determinant. You may remember this from a linear algebra course, or perhaps even from a college algebra or an Algebra 2 course from high school. The way you do a determinant is, I always learned it visually, is that you multiply down along this diagonal. So that's A1 times B2, and then you subtract, multiplying it up along the other diagonal, A2 times B1, or B1 times A2. And that's a determinant of a 2 by 2 matrix. We're going to be working with 3 by 3 matrices for more of what we're doing, but we need this component in this discussion. So let me take a look with you at a 3 by 3. So if you have a 3 by 3 matrix, you can't just go along the diagonals in quite the same way. So what you do is you do something that's called expanding along minors. And so you take the first value, A1, and then you use these four components to create your determinant. That's a 2 by 2 determinant. And then you use the middle one, A2, and it sort of blocks out the row and column, and you use the remaining pieces, B1 and C1, B3 and C3, so you see that component right here. And then you use A3, again it blocks out the row and the column that it's on, and it uses these four pieces, B1, B2, C1, C2 to create a determinant. And then once you have those 2 by 2 determinants, you do the determinant the way you did before. So you multiply down, you subtract, and then you multiply up. Now do notice that expanding along minors gives you a positive here, a negative in the middle, and then a positive at the end when you're creating this. So to start with, we're going to we're going to find a determinant. And so the determinant we're going to find is for this particular matrix. So we're going to start by taking this top corner right here, the number 2. So this is 2 times the determinant right here in this component. So that's 1, 0, negative 1, 1. And then we're going to take the middle component, which happens to be 0. We'll go ahead and write it down. This would be subtraction of 0. I know it's just going to be 0, but just for the practice of having done so, that means we cancel out this row and column, so we create the 1, negative 2, 0, 1 determinant. And then the last one is addition of the last fact, which is actually a negative 1 right up here in the corner. So it's negative 1. Sorry, I'm running out of space here. Give me just a second. I'll move it over when I'm done. And then this particular corner of this matrix. So 1, 1, negative 2, negative 1. Alright, I'll just move it down here. That'll work. Alright, and then we would go along the diagonals. So this is the value 1. So I've got 2 times 1, and then it would be minus 0. This middle value is just 0. And then we have minus 1 times, and we'll go along this diagonal. This would be negative 1. And then minus this diagonal would end up giving me a positive 2. Oops, those are not supposed to be like absolute values. Those are parentheses now. So in the first piece I get 2 times 1, which is 2. And then on the back piece I actually get a positive 1, and then I multiply it by a negative, so I get a negative 1. So this determinant ends up being a value of 1. So how are we going to use this determinant? Well, we're going to use this in the definition of the cross product. So for two vectors, A1, A2, A3, and B1, B2, B3, in vector space 3, we define the cross product, or sometimes called the vector product, of A and B to be this component, ijk along the top, and then you see the vectors. So here's vector A, and here's vector B. And then we expand along those corners. So here you see the I from this corner, and you see these four pieces of the matrix right here. And then you see the J right here along this one, and you see these four pieces along this for the matrix. And then you see the K right here, and you see this corner right here along this for the matrix. And then again, just like all the other ones, we would go through and we would do the individual 2 determinants on that. So the determinants of size 2 rather. All right, and one theorem before we go on to actually compute a cross product. Theorem says that if we have any vector and we do its cross product with itself, it's going to be equal to 0. And if we do the cross product with the number 0, it turns out 0. I think this is probably a pretty clear and easy one, but the same thing is going to happen here. We're going to actually get the components to sort of add to 0 in the right places to give us a 0 vector. So let's go ahead and find a cross product so you can see how it works. So we set up a 3 by 3 determinant with I, j, and k. The A vector is going to go in next. That's 2, -2, and 0. And then the B vector, 3, 0, and 1. So to start with, we're going to do the I component. It's going to be the bottom corner of this determinant. So this is -2, 0, 0, 1 times I, minus, and then we're going to do the outer components. So the outer, to get my outer vector, which is going to give me 2, and then 0 underneath k, 3 underneath I, and 1. And this is times j. And then we have a positive, and we're going to get the left corner, which is 2, -2, 3, and 0, and that's times k. And then each one of these is going to be expanded. So this is actually going to give me -2, and then technically minus 0. I'll write them in for this one just so you can see it. Minus, and again, this one's going to give me 2, and then minus 0, because 3 times 0 is 0. J, plus. This one's actually going to give me 0, and that's going to be minus a -6. So this would be plus 6 times k. And we're going to simplify. So this gives me -2i minus 2j plus 6k. Or you can write it in component form, because we were given the problem in component form if you prefer. -2, -2, 6. Either way is fine. We dealt with some issues about orthogonal, which is the same thing, of course, we said as perpendicular back in section 3 with the dot product. We actually have a property related to that with orthogonal vectors as well, with cross product. So any 2 vectors, A and B, in vector 3 space, A cross B is actually orthogonal to both A and B. So in other words, if we took A cross B and did a dot product with A, or A cross B and did a dot product with B, we would actually end up getting that the dot product is 0. So they're orthogonal vectors that we're finding. This A cross B is an orthogonal vector to A and B. And the right-hand rule tells you how you figure out the direction. So if you align your fingers of your right hand, it is important to be a right hand, this is the right-hand rule, along the vector A and B, and you bend your fingers around in the directions of rotation from A towards B. So initially your hand, if you sort of have it open, your fingers are pointing out in the direction of A, and your hand or your arm that's coming back at you is in the direction of B. And then if you move your fingers and you curl it around towards B, as long as you're rotating through an angle less than 180 degrees, then your thumb will point in the direction of the orthogonal vector to both of the vectors that you were working with to begin with. It's kind of like putting your hand along like the XY axis. And obviously if you put your fingers on the X part and your arm on the Y part and you rotated your fingers around from the A, or the X axis around to the Y axis, your thumb would be pointing upward, and your thumb pointing upward would be the orthogonal vector, or the Z axis in that case. So we're going to find 2 unit vectors that are orthogonal to the given vector. So the idea that it's being orthogonal means that we're going to find a cross product. So that's where we're going to start. And then we'll make them into unit vectors instead of it just being any particular cross product vector. So we're going to take I and J and K, and we're going to take the vector components 3, and then J is -1. There is no K, so it's 0. And then we have no I in the vector B. We've got a 4 in the vector J, or 4J in that vector, and then we've got a 1K. So we're going to expand along the minors here, and so this is going to start with the I component. So we have -1, 0, 4, 1, I, minus, and then we're going to have 3 and 0 from underneath I, and then 0 and 1 from underneath K, and this is times J. Then we're going to have plus, again 3 and 0 underneath I, and then -1 and 4 underneath J. And this is times k. We're going to do each of the individual components. So we've got negative 1, and then it's minus 0 times I, plus we have 3 minus 0 times j. I'm sorry, that was not a plus. Let me fix that. That's a minus right there. Let me get my sign right. The next one's a plus, and then we have 3 times 4, which is 12, and then minus 0 times k. So lots of zeros in this one. This gives us negative 1i, or just negative I if you like, and then it gets us minus 3j, and then plus 12k. And then in order to create a unit vector, of course, we need to figure out what the magnitude of the current vector is that we have. So this is A cross B, and I want to know the magnitude of A cross B. So this is the notation. So this is the square root of 1 plus 9 plus 144, and that's 12 squared. This gives me a square root of 154, which actually doesn't simplify if we try to do it, but that's my unit, or my magnitude currently. I want to create a unit vector of that from that magnitude. And so my unit vector, my first unit vector I should say, is going to use this square root 154. So it's going to write square root of 154 over 154, and it's negative I. And then I'm going to have minus 3 square root of 154 over 154 j, and then plus 12 square root of 154 over 154. Now, as you can tell, some of this is going to simplify. For instance, the 3 and the 154 here, those reduce. Okay, so not the 3 and 154, I was meaning the 12 and the 154. They're both even, so they'll divide. So this 12 will actually become a 6, and the 154 will become a 77. So this is one unit vector, and we talked in the last section about how to create a second unit vector. The second unit vector we're going to create, and I'll move some of my type on the screen so that we can actually have space for it, is to just take the same unit vector we already have and then just multiply by a negative through it. So if I do that with this particular problem, I will end up having, so another unit vector would be the square root of 154 over 154i plus 3 square root 154 over 154j, and then minus 6 square root 154 over over 77. There we go. Okay. That one, I forgot the k on the second one up there too. All right. So those are my 2 unit vectors. All right, theorem 4.3 tells us all the different properties that hold for cross products. The order of the cross products isn't quite commutative. It's sort of backwards. You have to take, if you take B cross A, you'll actually get the exact opposite, the negation of A cross B. And if you think about it in terms of the vectors we just created, that makes sense. So when we were talking about describing how your vector points, I was using the x, y, and z axis. And of course, the z-axis pointing up would be orthogonal to the x-axis and the y-axis, but also the z-axis pointing down would be orthogonal to them. So that gives you the negative, sort of the opposite vector that you're looking at there. You also see the next one, a kind of an associative property. Looks to me like maybe there's a typo going on here on problem number 3, so I'm sorry about that. That one should be a parenthesis there, not here. So that's a distribution property, and another distribution property on part 4. And then we have a dot product, cross product kind of combination going on number 5, and even again on number 6, and the relationship that sort of extends to combining those two. Now, just like when we did the dot product, we had a alternate equation that came about for finding the cross product. The same thing is true, or for the dot product. The same thing is true for the cross product. So if you have any two vectors in vector 3 space, an angle between them is theta, and again, theta is between 0 and pi. Then when you do the cross products, it's the same as taking the magnitude of A times the magnitude of B times the sine of theta. And obviously, there are certain values for theta that would make this equal to 0, just like for the values of theta back when we had cosine of theta in the dot product. In particular, if you take a look at the corollary, if you have two non-zero vectors, they're actually parallel if and only if the cross product is 0. And if you take a look back here, the cross product would end up being 0, the theta value, at theta equal to 0, or pi, or 2 pi. because those values are the ones that make sine equal to 0. The sine of 0, sine of pi, and sine of 2 pi are all 0. So obviously, if the angle between something is nothing, it's the same vector, or parallel vectors. If the angle is a pi between them, it's going to lie on a line, so it's going to be the same kind of vector, and the same thing for 2 pi. Theorem 4.4 also gives us an interesting geometric interpretation of the cross product. For any two non-zero vectors, as long as they're not parallel, they'll form two adjacent sides of a parallelogram. And I'll draw you a picture for that. Let me finish reading first. Notice that the area of the parallelogram is given by the product of the base and the altitude. Thus, the area equals, and we've got this formula. So I think a picture is in order to sort of explain what's happening. So let's imagine that this is vector B down here, and this is vector A. All right, so it's saying that they form the sides of a parallelogram, and so we're going to draw that parallelogram in. And so we can extend this side over here. We can extend this side right here. I think that needs to be extended a little bit further. And we have this parallelogram here. Now this parallelogram is actually determined, the area of a parallelogram that is the base times the height, and the height is actually the altitude. We call it the altitude so as not to get confused with maybe like the side length. So here's the base listed, of course, as B, and then the altitude is this piece right here. I'll just draw it in blue. This is the altitude. Now, we can actually, oh, and here's the angle theta in between. We can actually create or find the side length based on the angle theta and the side A. And so the side that we're working with, or the angle theta, it would be the opposite over the hypotenuse, which is a relationship of sine. And sure enough, this would actually end up being, when we solved for it, let me write that down so you can see it. So the sine of theta would be A over our new side, our altitude. Sorry, this is being written on top of what I already have. I didn't leave myself enough space in this problem, obviously. So here's sine of theta equals A over the altitude. And if I solve for the altitude, then I would actually, I'm sorry, I have the altitude this side, A backwards. Let's try this one more time. So this would be the altitude, because that is the opposite side, over the side A. And then if I multiply by A, I'll solve for the altitude. So this length right here that's in blue is actually the value A, or the magnitude of A, its length, times the sine of theta. So if you take this area formula base, which is actually B, and then you multiply by the altitude, which is the A sine theta, you get, in no uncertain terms, the exact formula that is A cross B's magnitude. So we're going to actually use this fact, and we're going to find a parallelogram. And it's a little bit, it's not really direct exactly, so there's a little bit involved in finding this, but it's definitely going to involve a cross product, obviously. So we're going to take the area of a parallelogram. The first thing that we need is we actually need to find the cross product. So we're going to do that first. So the cross product, we'll call this vector, I guess A and B will work on this just fine. Notice it's in 2 dimensions, and what we're working with is only going to work in 3 dimensions. So we're going to add a component of 0 to the end of it. So we're going to do A cross B, which is going to be I, J, K. It's going to be 2, 3, 0, and 1, 4, 0. And notice you've got some zeros in there, so things are going to be cleaning up a little bit as we go. So to start with, we've got 3, 0, 4, 0 times I. We've got minus, and then we've got 2, 1, 0, 0 times j. And then we have plus 2, 3, 1, 4 times k. Now, both of these that have the 0 column in them are going to give me a cross product of 0, so we're not going to get any i's or j's. The only thing we're going to get is from the k component, which is going to be 2 times 4, which is 8, minus 1 times 3, which is 3 times k. So we get a vector 5k, and if we had to do so, we could actually write a formula, but we can see then that the magnitude of this vector 5k is 5. So we can use that information to find the area of our parallelogram. Look back over here. The area of the parallelogram is the magnitude of A cross B. So my area of this parallelogram that it's describing is exactly the A cross B that we had before. We don't even have to use the information about theta. We just used that to establish why this is the dot product. Here's another interesting application of our theorem 4.4. It allows us to find the distance from, that should say from, a point to a line in R3. So if you let D represent the distance from a point Q to the line through the points P and R, then from trigonometry, the distance would be equal to the magnitude of PQ times sine of theta, where theta is the angle between PQ and PR. And then we've got a formula, but I think, again, just like we did before, a picture is in order to help explain what we're seeing happening here. So we're going to put this vector on bottom, and we're going to put a vector over here on top, I don't want you to think it has to be a right triangle, so we'll go like this to give you a little bit different image than we had before. So this right here is P, because I need to have a Q and I need to have the R, which is up here and over here in our problem. And then the angle theta, of course, is between them. And so we're wanting to sort of drop a perpendicular and find the length right here, because if we want the distance, we want the distance from point P to the perpendicular that's going on. So this right here, again, using some trigonometry, we would find out that this is PQ times the sine of theta. And again, it's the magnitude of PQ. I'm running out of space, but there's the magnitude of PQ right there. So if we took the cross product of PQ cross PR, that would be the same as the magnitude of PQ, magnitude of QR times sine of theta. And the magnitude of PQ times, oh, there's a typo, that should say PR. I'm sorry, that's PR. The magnitude of PQ times sine of theta is D, which leaves us with the PR right here, which is correct. And then I've got the PQ times the PR magnitude, right, divided by the magnitude of PR if I were to divide to get this solved for D. All right, so we're going to use this fact and we're going to find a distance. So here are three particular points. Q is the point we're looking for. It says find the distance from Q to the given line. And they don't give us a line, they give us 2 points on the line, and then we're supposed to use that to find a line. So we're going to start there. We're going to actually first identify what my PQ and my PR are going to be. So PQ is going to come from, this will be P, all right, just a moment. All right, I think I have a letter mislabeled. I think back over here when I told you that that was actually QR, I think it is supposed to be Q, and this one was supposed to say then QR. That's the only thing that would make sense with what we're working on in the next place. So PQ cross QR that we're working on. All right, anyway, over here, so we have PQ and we have QR, I believe. I don't have my book with me to verify this, so you guys can double check on that. But we've got PQ here, which is created by taking P to Q. So this is going to give me a vector that's 0 because I've got 1 minus 1, another 0 because I've got 3 minus 3, and then negative 2 minus 1, which is negative 3. And then QR would be the other point. So here's the point R over here. And we're going to go from R back to Q. So again, I'm going to get 0. 0 minus 3 is going to give me negative 3, and then negative 2 minus 1 is going to give me another negative 3. So these are my two vectors that I'm working on. And then I need to do the cross product for these. So the PQ cross QR, which is going to be the cross product of these guys. So we've got I, J, and K, and we've got a column of zeros, which is quite helpful in terms of computing because I'm going to have a lot of zeros coming into play then. And if we take a look at this, we're going to expand along the I column, so I'm going to get 0, negative 3, negative 3, negative 3, I, and then minus 0, 0, and then negative 3, J. And then my last piece is plus, and then I've got 0, 0, 0, negative 3, K. And so anything with a row of zeros, and both of these have them, is going to be eliminated. The only thing I'm going to end up with, end up getting, is actually going to be 0, and then I've got minus a positive 9, so minus 9i. So this is actually negative 9i. So that's my my cross product, and that means then that PQ cross QR its magnitude would be 9. All right, PR then. PR's magnitude itself, QR, sorry, let me get the right letter. QR's magnitude itself is going to be hang on just a second. Okay, we're going to go back and we're going to fix the problems. This is my fault. I had it right the first time, and then I questioned it and messed it up. This is, in fact, going to be PR, just like it was listed, and I had it right. So this is PR. I didn't label my points, which I think was causing the problem. So we're labeling PR down here, and this is going to be fixed. We're going to get this all fixed right quick. So give me just a second. We'll erase it, and we'll start over this piece. Okay. So we did the point P to Q, and then I need the point from P to R, which was my other one. So if I start with R and go back to P, I'm going to get 0. And then I've got 0 minus 3, so that's negative 3. And then I've got negative 2 minus a negative 2, which is 0. There we go. All right, so I need the cross product of PQ cross PR. This is what happens when you start questioning your own notes. They were all just fine to start with, and I started thinking they were wrong. All right, so I need the cross product. So this is I, J, and K, just like we did before. Got a lot of zeros, even more than I thought I had before, right? And so we're going to expand along these corners. I've got 0, negative 3, 0, times I, minus 0, 0, and then negative 3, 0, times j, which is going to give me 0, and then plus 0, 0, which is going to give me 0, negative 3 times 0, k. And so, like I said before, this one's going to give me 0, this is going to give me 0. This piece right here is going to give me 0 minus a 9, so this is negative 9i. And then clearly the magnitude then of this, of PQ cross PR, its magnitude without even, computing it directly is actually going to be 9 because the length of the vector negative 9i is 9. Now, the other piece that we needed to do is we needed to do, let's see, PR's magnitude. So the magnitude of PR itself, well, PR is down here, and so its magnitude would actually be the square root of, negative 3 squared, if you wanted to write it out, or you could just recognize that it's also 3 because it's only negative 3i, so it's 3, which means that when we find the distance is the magnitude of PQ cross PR divided by the magnitude of PR. So this is going to equal 9 over 3, or 3. So we end up getting the distance of 3 away from the point Q to the line that contains the points P and R, or to the line PR, you could say. All right, one other question we're going to work with, again, back on a little bit with angles. It says use the cross product to determine the angle theta between the vectors, assuming that the angle is between 0 and pi halves. So doing this problem is going to be requiring us to use the cross product and to use the formula for the cross product that has the theta in it. So this is going to be A cross B is equal to the magnitude of A times the magnitude of B times the sine of theta. So in essence, we're going to do both sides of this equation and plug some values in. So we're going to start out with the A cross B. So this is I, J, and K. I've got 1, 3, and 3, and I've got 2, 1, and 0. So we've got the vector 3, 1, 3, 0 times I minus 1, 2, 3, 0 times j plus 1, 3, 2, 1 times k. And we're going to multiply. So I multiply down, I get 0 minus 3, so this is negative 3i. And then I have minus, this is 1, and then it would be minus 6, but then the minus here would make it a plus 6j. And then we've got a plus. I've got 1 And then I've got minus 6, so that would be negative 5. So we'll take this positive and make it a negative, so this is negative 5k. And then we need the magnitude of that, so we need the magnitude of A cross B, which would be the square root of 9 plus 36 plus 25, which is the square root of 70. And that doesn't reduce. And then we need the so that we've got the left-hand side here now. We need to find the magnitude of A and the magnitude of B, respectively. So the magnitude of A would be the square root of 1 plus 9 plus 9, which is the square root of 19. And the magnitude of B would be the square root of 4 plus 1, which is the square root of 5. So if I take this formula, then I've got square root of 70 equals the square root of 19, square root of 5 sine theta. And if I divide both sides by the square root of 19 square root of 5, and then I'd use the inverse sign, I would end up finding that theta equals sine inverse of square root 70 over square root 19 square root 15. And if you evaluate that with your calculator, you find that the theta equals 1.03 for that one.